Welcome to this explainer. Today we're going to demystify something that usually gets treated like some kind of futuristic magic. But honestly, in reality, it's a highly systematic, step-by-step transformation of information. We're exploring the machine learning lifecycle, and we're going to walk through the incredible journey of how raw data is refined into actual, actionable, intelligent decisions. So let's hook right into this by posing a massive, fundamental question. How exactly do computers learn without being explicitly programmed to do so? I mean, historically, software relied on incredibly rigid rules, right? Like, if X happens, then do Y. So how on earth does a system actually improve its own performance over time just by looking at information? Okay, let's dive into this. Machine learning is a foundational branch of artificial intelligence. It basically enables systems to learn directly from data, identify hidden relationships and patterns, and, here's the kicker, actually improve their performance over time without relying on explicit, hard-coded programming. So instead of giving the machine the exact rules, we just give the machine the data and it figures out the rules all by itself. Pretty amazing, right? Here is our roadmap for today. We're going to build a model together, chronologically. We'll start with the types of machine learning, then move on to key machine learning algorithms, prepping and exploring data, evaluating model performance, and finally, we'll wrap up with real-world applications. Let's get to it. Kicking things off with Section 1, Types of Machine Learning. Now, with supervised learning, you're training on labeled datasets. You're mapping known inputs to exact outputs. Think of it like a teacher guiding a student, feeding a system images and explicitly defining the target. Unsupervised learning, on the other hand, tackles entirely unlabeled data. It's kind of like exploring a new city without a map. It forces the model to uncover hidden groupings, correlations, and intrinsic structures completely on its own without any predefined target. But wait, actually, scratch that. It's not just a binary choice between supervised and unsupervised. There are actually a total of 3 primary learning paradigms in this vast ecosystem. Let's look at all 3 together. We've got supervised learning with its labeled data and unsupervised learning with its unlabeled data. But our third paradigm? That is reinforcement learning. This is a fascinating area that focuses on training autonomous agents to make sequential decisions by interacting directly with an environment. The agent basically learns through trial, error, and receiving rewards or penalties based on its actions. Believe it or not, it's exactly how we train self-driving cars to navigate traffic, or even bots to play incredibly complex strategy games. Moving right along to Section 2, Key Machine Learning Algorithms. Now that we understand the learning types, let's look at the actual engines that drive these systems. And this brilliantly illustrates our foundational engines. First, decision trees, which offer highly intuitive, rule-based, recursive branching. Next, if you need robust classification, support vector machines step in to find the absolute optimal boundaries to separate complex classes. And finally, for capturing incredibly complex, nonlinear relationships, neural networks use interconnected layers inspired by the human brain. They literally form the absolute core of modern deep learning. Okay, Section 3, Prepping and Exploring Data. Because honestly, even the best algorithms fail if the data isn't prepared. So here is the messy reality check. Raw data often contains noise, inconsistencies, or missing values. In data science, there's a golden rule: garbage in, garbage out. If we don't address data quality issues right off the bat, our sophisticated machine learning models are going to produce inaccurate or highly unstable results. Preparing the data isn't just some administrative chore. It is the absolute foundation of reliable AI. We tackle this messy data through a strict pre-processing pipeline. Chronologically, we start with imputation to handle missing data, like perhaps swapping a blank value for the statistical mean. Then we apply normalization and standardization. This basically scales the data so all variables play on a level field, preventing a model from getting completely confused by mismatched units. Finally, we finish up with outlier detection, isolating extreme values that could completely skew the model's understanding of what normal patterns look like. Section 4, Evaluating Model Performance. So we have an algorithm and clean data, but how do we know if our model is actually smart? Now, what's really interesting about this slide is that different types of machine learning problems require entirely different report cards. If you're performing a classification task, say categorizing an email as spam or not spam, you evaluate it using metrics like accuracy, precision, recall, and the F1 score. But if your model is performing a regression task, like predicting the exact dollar price of a house, you look at error-based metrics like mean absolute error or R squared to see how far off your continuous predictions actually are. Evaluating your model properly ensures you're measuring what actually matters for your specific business goal. To truly understand classification performance, data scientists rely heavily on something called the confusion matrix. It's basically a simple table comparing the actual true labels in the dataset with the model's predicted labels. It breaks all the results down into true positives, true negatives, false positives, and false negatives. This is incredibly powerful because it lets us pinpoint exactly what specific types of errors the model is making. Like, is our medical diagnostic model accidentally flagging healthy patients as sick, resulting in a false positive? Or is it letting a sick patient slip through undiagnosed, which is a false negative? The confusion matrix gives us this absolutely essential visibility. Finally, Section 5, Real-World Applications. Let's see how this entire life cycle builds towards solving actual business problems. So the crucial point is that mastering this life cycle isn't just some academic exercise. It's about massive real-world impact. I mean, supervised learning alone powers the spam and fraud detection that secures our digital lives. And it drives the credit risk assessments at major financial institutions. It's scaling complex decisions every single second, from medical prognoses to global supply chain forecasting, right down to predicting customer churn. It's literally everywhere. Which brings us to a final provocative thought. We've seen the life cycle, right? From raw, messy data all the way to evaluated, deployed decisions. So as machine learning models become increasingly autonomous and capable, what complex problems in your industry will you solve using data? The paradigms, the algorithms, and the metrics are all there, just waiting for you to use them. Thank you so much for joining me on this explainer, and I really hope you leave feeling empowered and ready to harness the true potential of the machine learning lifecycle.